Hello everyone, I am Pushpita Chanda. I'm a PhD student at IIT Delhi under IIT Delhi and University of Queensland joint PhD program. I'm the TA for this course, Introduction to Optics. So let's begin this class. So today is basically the week where optics can be applied has been discussed in this course. So hence the name applied optics. So in basically in the applied optics degrees, we start from here. So the main things is this anti-reflection coating, optical fiber, how can we build a laser, holograph, um, and uh, and all those things. So it's just the beginning of the topics. So if anyone is more interested, they can go through the what's mentioned in the reference of the classes. They can learn. So anti-reflection coating is basically a coating above glass. So for normal things, there would be a reflection and a refraction. So this reflection part is the like waste or the amplitude of intensity of the light is being reduced due to this reflection part. But if we it's on reflection part and then reflection. So this two being we can like determine the D here such that and also the N of F of the refractive index of index of the layer. You can choose them so that the density that is the basic idea behind the anti-reflection coating. So how to cancel each other? We already know that we start from the reflection like of then this is actually basically this is reflected position. This is into the advance improvement one plus into transmission is basically 2 and 1 by m plus n1. From this we can see that for glass and air, the reflection loss is also in calculation. If this is the way 1, this is 2, this version 3 is 4 and 5. If we choose an F and these are the way 2 and 5 cancel out, then we can say that this is basically and so we know this distance is basically 2 into NFD should be equal to equal to 2 for minimum to get the distance. We see the 5 should be canceling each other and their calculation has been so I'm not repeating that. So how do we choose an F from that calculation? We got to know that an F should be equal to an A and G. So when we are talking about air and glass, here N1 and N2, air and glass interference, and A is 1 and N glass is 1. So that is basically if we calculate 5, so that is almost equal to 1.247, something like this. But if we change the glasses, we presume that refractive index for glass is 1.5, but it is not the case all the time. Then this NF changes like, and also mathematical calculation, we got to know that p value from this we can see that d is basically lambda by 4 NF. But we also know that this is the if d lambda by 2 or lambda plus lambda by 2 or 2 lambda plus lambda by 2 all give this. So can we that d value can be equal to lambda 4 NF. When it can so if lambda by 4 NF, it can as well be 5 lambda by 4 NF and so on and so forth. Can be written as plus by 4, where n start from 0, 1, 2, and so some kind of question regarding this anti-reflection coating. So what would be kinds of the reflection of refractive index, that is minimum thickness of refractive index 0.6 for a light of wavelength 62 nanometer for normal incidence. So for that we know D is basically lambda by 4 NF. So lambda is 632. Here it is nanometer. 4 into 1.46. Here NF is given, but there can be questions where NF is not given, but the refractive index of glass is given, or in the glass is in the oil, then refractive index of oil and glass will be given. Then you can calculate NF as NA and NG and put this. So here the answer is 1081. To So I'll discuss question if I get something. Now just move on to this next holography. So there are no, basically almost none, uh, holography, mathematical holographic question, but you need to understand the concept very much. So in holography, basically there is a photographic film, and we capture both amplitude and phase. So you can always capture it as intensity variation, but here the amplitude and phase has been captured as the intensity variation. So here is another question. And question number 2. Find the thickness and refractive index of an anti anti reflection coating is necessary for glass lens in air at equivalent 590 nanometer. So that is 1.5. We need an F, which is, like I said, NA and G, and no 1.1 into 1.5, that is 1.225. So it is not necessary that we mention all the lenses have respective length. Thickness required is equal to T is equal to lambda by 4 and here the lambda is given 590. So from that, it is very clear that for different lambda thickness will be varied. So for which application for which lambda we are using that anti-reflection coating, it's very important. So you can see these things properly. It has been used in our like classes where we say the blue cut and all those things, or the anti-reflection putting on the coating that will block the blue rays will not block the other light because of the lambda motion here. So the reflection coating will work perfectly well for you. The light will not go for it. So that will be 124 nanometer. So now we continue our discussion in the holography. So in holography, basically amplitude and phase information is being stored as intensity variation information. So here both the both the information has been stored as a matter of fact, say information uh, in the interference. Basically, that is the case. For the holography, amplitude and phase both are important. So first, the holography, also recording of holographic two-part, and another is reconstruction of. This is the two-part of holography. Reconstruction of holography. Of holography. So for recording of holography, so there first we see the inline holography, but here there is problem that the real image and virtual image is aligned, so you cannot like distinguish between these two. Then we came to the different type of holography. So there are some limitations. Then we move to the different type of holography, which is off-axis holography. So here are separated. So in both ways, what happened that in the photographic plate, in inline holography, what happened that there is a object, so the light comes from here, and it also have a reference beam. Reference beam plus transmitted beam, it falls here, or scattered. Sorry, reference beam plus scattered beam. So we record the holography, then when it comes to, this is basically object. So when we want to reconstruct the holography, then in the place of object, we'll place the hologram, and here, this is the hologram, and we again bombard it with reference beam. Then we get a real image and virtual image. The virtual image is here, the real image is there. So the virtual, we are aiming for the virtual image. For off-axis holography, the photographic plate is like this, reference beam is coming like this, object beam like this, and then when we want to reconstruct the hologram, then again we for reference beam, let the reference beam for the photographic plate like this. We will get a real image here and the virtual image here. So now, um, so basically these things has been clearly discussed in the class and more precisely. There are different part of holography, like that holography depends on which photographic plate is being used, and so on and so forth, and how to calculate the like holographic intensity and all those things. There, if someone interested, they can go in deeper. But for this course, this is enough. Whatever I've discussed in the class. Now we basically go to optical fiber. So this is a very important application of optics. So we all know. Sorry, the class has dropped. So basically, the optical fiber. So optical fiber is used to guide light from one place to another. The basic simple work of optical fiber is that. Mm. Here, when we say light, so light basically all the electromagnetic waves. That's the concept. So we'll discuss that there is some core, then cladding, and when we see optical fiber, they are very, and we'll see this distance is very small. And it's actually a science to couple optical waves into this tiny distance. So we will not get into that deep in this course, but whoever from the participants here will pursue the applied optics in future or this optical fiber optics in future, they can see that this is very precise calculation, very precise angles, very precise wavelengths, and how to couple the light inside this. It's not very difficult with current state of art facilities, but it's not either as simple as like it's not like obvious. And when you see optical fiber, you will see some like width, but when you do calculation, you will see that they are in very small, like in microns. So how come that width comes? So because over the core and cladding, there is some coating, then there is strength materials, and then there was outer jacket, and that make some millimeter, centimeter length. Okay. So in optical fiber, the phenomena we use, that is total internal reflection. And another thing, there are different kind of modes, transverse modes, like uh, longitudinal modes, transverse modes, and there is TM modes, are different kinds of modes, like where XY mode, like in both direction there are modes. So each mode has different like coupling coefficient and all those things. So like I said, we don't need to worry about those things. They are for future. So I'll only cover the portion in the class it has been discussed. So the total internal reflection has been done. So we know that for total internal reflection, light needs to go from denser to rarer medium. And you will also see that the rarer means denser to rarer means not from 1.5 to 1. Active index difference is like 0.01, sometimes 0.001. So that is the case actually. So you know that it's like straight line. So this is cladding. This is core basically. This is the axis basically. Cladding, so the light enter like this, then they go like this and this and this. So this is I, and this is theta, and this angle phi, it needs to be critical, and so on so forth. So for that to be a critical, so it's basically we can control I. So that phi is basically critical. we need to choose N1 and N2 so much that if this is N1 and this is N2, so delta, which is a parameter, which can be N1 square minus N2 square by 2N1 square when N1 is almost equal to N2. This is equal to N1 minus N2 by N. And they are basically multimodal fiber. Not only one mode is allowed, every TM mode and TEO mode. So there are TE mode, transverse electric field, electric mode, TM mode, transverse magnetic mode, TE mode, transverse electric mode. So forth. So if we use silica for cladding, then N2 is 1.45 and delta is 0.01, then N1 is given 1.465. So say 0.015 difference between N2 or N1 minus N2. That's the difference between cold and flattening. So if we calculate all those things, that what should be the value of sin I and all, because that is the value we think is in our control, the I value. So sin I needs to be less than N1 square minus N2 square minus N0 whole square under root. So when N0 is equal to 1, N0 is here, N0 is equal to 1, then sin I is basically, you can say N1 square minus N2 square. So it is the condition when N1 square is less than N2 square plus 1. If N1 square is greater than N2 square plus 1, then sin I needs to be 1. That means I is negative. So the numerical aperture, the value for the fiber is given by this parameter N1 square minus N2 square. So here basically N1 square is greater than N2 square but less than N2 square plus 1. So you can get the thing that what is the difference between N1 and N2. And there would be attenuation when we transfer data through the optical fiber. That attenuation part is given by alpha, which is the log scale, log 10 base P1 and P2. P1 is the input, P2 is the output. And we prefer the attenuation is super lower in the optical fiber. And the another problem is pulse dispersion. And the main two reasons are because the angle I is different for different ray, and another is the velocity is different lambda velocity or time velocity. Like we know that uh, the refractive index, uh, the different lambda sees different refractive index, and due to this, the velocity of them also changes. So there are diffraction problem and all those things. So for that pulse got dispersed and how we like compensate that pulse dispersion, that is another topic. But the very easy way like is to solve using graded graded index optical fiber. So the refractive index changes as in square is basically in one square 1 minus 2 delta r by a whole square when it is r is less than 8. That means this is score and cladding is basically 2 square, which is equal to in square 1 minus 2 delta by r is greater than a. So we use graded index fiber to minimize the dispersion and attenuation and all those things. So different because of this, there is a time interval of deviation. So if even we put all the input at the same time, the output have a time interval duration, which is n1 by L, the length of the optical fiber, by C, n2 by n1. This is a graded index optical fiber, and you already know the ray path. Ray path in parabolic index media, and that ray path is basically x function on side if this direction is said, and sorry, this will not be there. So the refractive index profile will be like this, or graded index profile, and this is in the x direction. So that would be a sine theta put over to delta sine n1 put to delta alpha beta bar into z. So beta bar is n1 was theta 1. And this is not alpha, this is a. So N1 and theta 1 varies so way that here in the graphing mixed media, beta is constant. And the applications for optical fiber is huge. It's when you in communication, medical, sensing, defense, and your all the 4Gs, like the internet connection, is due to a huge bunch of optical fibers running in the seabed, ocean bed. Due to this, there's all the connection. Even if we switch to quantum communication and all that, we do need optical fiber for quantum key distribution. So now we'll go to some question answer. Question 1. An optic fiber of refractive index 1.5 is to be clad to ensure TIR that will contain light traveling with in 5 degree of the fiber axis. What minimum RI is allowed to allowed for the cladding? So here basically this is core, this is cladding. The core is 1.5. So the when they say an optical fiber of refractiveness 1.5, that means core is 1.5. And when you send the angle, this is actually okay. So this is a fiber axis. This is 5 degree. So how we say that they do? So basically, this should be 90 degrees because the total is reflection. And by the virtue of geometry, this is 90 degrees. If this is 5, this is 85 degrees. Then N1, the answer is N1 sine 85 degrees is equal to N2 sine 90 degrees. So N2 basically N1 into sine 85 degrees. So N1 is 1.5 and sine 85 degrees is 0.996, which make it 1.494. This is the answer. The cladding should be 1.494. See, the difference is 0.006. Question number 2 is the angle of acceptance of an optical fiber is 30 degree when kept in air. Find the acceptance angle when the same fiber is immersed in water of 1.33. So when n naught was 1, acceptance angle theta A was 30 degree. So when n naught is 1.33, what would be the acceptance angle? So the NA, so this value is basically sine theta A. When we look at the like calculation, this is theta, this is theta, this is the acceptance angle. So in the calculation, we'll get to know this come from the cos theta part, and this is basically sine theta can be in the calculation. So that is so this is 1 into sine 30 degree. So basically numerical aperture remains same. So that would be equal to 1.33 in the water sine phi A. So sine phi A would be sine 30 degree by 1.33. So phi A would be 22 degree 4 minutes. So the acceptance angle got reduced when from the air we immersed in the water. So this is n naught. So n naught changes from water, air to water. There is another parameter called V number. So that is basically pi d by lambda into the aperture. And the d is the diameter of the pore. So there is a question. Is calculate. So why this V number matters? Because this V number will determine which TEM mode and TE mode will be allowed. So that's something like this. Calculate the V number for a fiber of core diameter 40 micrometer and refractive index of 1.55 and 1.5 respectively. For its core and cladding in a light of wavelength 1400 nanometer is propagating. Also calculate the number of modes that fiber can support for the propagation. So that is basically v squared by 2. And that value, how we came to that value, that's another kind of practical. So, V is equal to pi d by lambda into A. So pi d by lambda into our N1 square minus N2 square. D is 40 micrometer, N1 is 1.55, N2 is 1.5, lambda is 1400 nanometer. When we put this value comes to 35.05. So this is the P number, and number of modes that we allow is V squared by 2, which is 612.5. These are the number of modes. Almost this is the number of modes the fiber can support. Question is due to attenuation. The attenuation in optical fiber is 3.6 dB per kilometer. What fraction of its initial intensity remain after so attenuation coefficient is alpha, which is equal to 3.6 dB per kilometer. Length of the fiber is 1.5 kilometer. So what fractional intensity? That means P output by P input. So alpha is basically minus 10 by L log 10 P naught P output by P. This minus is because we have interchanged here. P1 was Pi and P2 is Po. When you change that, you can put a sign minus before the log. So after doing all this calculation, P output by P input is 10 to the power minus alpha L by 10. And now we could put the value alpha is 3.6 into 1.5 by 10, that is 10 minus 0.54, so 0.2. So 29% of intensity is received after 1.5 kilometer. So our attenuation is, when our goal is, it needs to be less. Now we'll go to the discussion for laser. So we know what does laser stand for, basically. Laser is basically light amplification. By stimulated emission of radiation. So LASER, that's called laser. So basically lasers are light source. Which are highly monochromatic. Highly coherent. And highly directional. So in the there are different courses in the NPTEL available, like Introduction to Laser, and then also there is a fast courses, fundamental optics for the attosecond science. So fast is very high level course. After this you can do the introduction of laser, which is a basic optics related course. There we discuss many kind of laser lasering thing. So that's also a 12-week course. So here we will discuss everything in brief, or some basic things in brief. So first is light matter interaction. And so why it's needed? Because that is how the emission process or stimulated emission process we will understand. So basically electromagnetic, atom can absorb electromagnetic radiation, and also it can emit electromagnetic radiation. So basically you see that if this is E1 and this is E2, atom got electromagnetic radiation come, atom absorbed it and it goes into the upper step E2. So what happens that the emission process can be like this. So Always remember when we draw that E1 level and E2 level, in the molecule there is no distinct E1 and E2 level. So basically the atom is in En level, and in molecule the atom, like the matter, the atom has an energy of E1, and at this at the, after absorbing electromagnetic radiation, it will have energy E2, but its position can be remain same in the matter. So these are to make understand the thing. So now it is in E2 here. So when it go to here, it will emit the electromagnetic radiation. So the stimulated emission is when that after one absorbing electromagnetic radiation, which is an E2, then come another electromagnetic radiation, and due to this, the atom make a transition and emit a electromagnetic radiation which has the same frequency. That is simulated radiation emission. So it is proposed by Einstein in 1970. So from that, Einstein also gave us two coefficients. So we know there are three Einstein coefficients, 1A2, B12, B21. So B12 is basically when the atom goes to from 1 to 2. This transition is given by B12. And A12 is the corresponding to the spontaneous emission. And B2, sorry, A12, not A12, this is A21. And B12 corresponding to stimulated emission. So the thermal equilibrium for that N1 B12 U function of frequency omega is the energy density, radiation energy per unit volume. Equal to N2A21 plus N2B21 U. From this equation, We also know n1 is n1 by n2 is e to the power minus what fraction of. So the ratio of n1 and n2, n1 is the number of atoms in the level 1 and n2 is the number of atoms in level 2. So e to the power e2 minus e1 by kBt. This is Boltzmann's constant. So this is basically h cut omega by kBt. So from that we get to know the radiation energy is basically a to 1 b1 to e to the power h cut omega kBt minus b to 1. So b12 is equal to b21 is equal to b. We can assume that, and we know from the Planck's distribution u omega is basically h cut omega cube n naught cube by pi square c cube 1 by e to the power h cut omega k b t minus 1. A to 1 by b to 1. If we compare this equation, is given by h cut omega cube n naught cube pi square c cube. And this is a relation between Einstein's two coefficients. And this is a thing you need to remember. So then we go to the components of laser. Components of laser is the active medium, the pumping source, the optical laboratory. So you know what is active medium is. The laser between the two mirrors, they are basically these two mirrors at the optical resonator. So this mirror is 100% reflective. This is actually semi-transparent, 99% reflective. So we have discussed this is optical cavity in the interference problem, multi-beam interference. So we took like advantage of that phenomenon. This is active media. And we need a pump for population inversion. So population inversion is very important. Like when the number of atoms at E2 is more than number of atoms at E1, this scenario is called population inversion. And that is very important uh, because after that, releasing of it will start. So active medium may consist of collection of atoms, molecules, or ions which is capable of amplifying light waves. Under normal circumstances, there are always a larger number of atoms in the lower energy state than in the excited energy state. In order to have optical amplification, the medium has to be kept in a state of population inversion. The pumping mechanism provides for obtaining a state of population inversion between a pair of energy levels of the atomic system, and when we have a state of a population inversion, the input light beam can get amplified by stimulated emission. So the optical resonator here. So what we need, that medium with population inversion is capable of amplification, but in order to that act as an oscillator, a part of the output energy must be fed back into the system. That's why we need a feedback system, and that is optical resonator. So there are different kind of optical resonator. You can like in the advanced courses, introduction to laser, you will see that there are different kind of optical laser, and there are some parameter G1 and G2 which needs to be between 0 to 1 for the resonator to be worked. Different kind of G1, G2 is function of R1, R2 basically. This is a plane parallel resonator example where R1 is equal to R2 is equal to infinity. There are concentric resonator where R1 is equal to R2 is equal to D by 2. There are confocal resonator where R1, R2 is equal to D. D is the distance between them. And there is spherical resonator, long radius. hemispherical resonator, signature, concave convex torus. This is the stability condition, which is the most stable resonator. Basically, we can dive into that like the extra class. So there is a two-level system. So in two-level system, this is E1, this is E2, and they have N1, N2. The number of atoms per unit volume which absorb the radiation is excited to the upper level will be N1, W1, 2, and the number of this is 1, 2. The number of atoms undergoing simulated emission from E2 and E1 be W2, 1, E2. So this is given by laser by uh, Ghatak and Thyak Razum. And number of atoms going through spontaneous emission would be T21, which will be radiative and non-radiative transition. So dN2 dt, the number of atoms changing with time, is W1 to N1 minus N2 minus T1 T2, and dN1 dt is basically W1 to N1 minus N2 plus T21 N2. So by the virtue of like conservation, the number of atom leaving N2 should be go to N1 or vice versa. So Tn1 plus N2 should be 0. So N1 plus N2 should be constant. So dN1 by dt at steady state, d1 by dt should be dN2 by dt. And doing all those, we can go through this calculation in the book. We get to the formula that delta n by n is equal to minus 1 by 1 plus I by I is. Delta n is n2 minus n. So I is the intensity I is when I is equal to I is, delta n become a function of I. And basically I is equal to I is when delta n is equal to half what is the corresponding intensity. So after all this calculation, alpha is given minus pi square c square omega square t spontaneous n naught square g omega delta e. So when I is less than I is, we have a loss problem. So two level system cannot have steady state population inversion. For that, we need to go to three-level system. Three-level system, the lazy happens in E1 and E2, and pumping happen between E1 and E3. This is the pump. This is rapid decay. And here the laser action happens. Remember, from the three-level system, there comes very question in the NEET of JAM GATE exams that which level has the least lifetime and which level has the more lifetime. So what happened here, that the pump is assumed to lift atoms from level 1 to level 3, from which they decay rapidly to level 2 through some non-radioactive process. This is the rapid decay. So N3 has the lowest lifetime. The pump, does the pump effectively transfer atoms from the ground level? Sorry. Pump effectively transfer atom from the ground level 1 to the excited level 2, which is now the upper laser level, and the lower laser level being the ground state 1. If the relaxation from level 3 to level 2 is very fast, then the atoms will relax down to level 2. Since the upper level 3 is not a laser level, it can be broad level, so that a broadband light source may be efficiently used as a pump source. So here, n is equal to n1 plus n2 plus n3. dn3 dt, the rate of change of like n3 is basically pump in Wp minus n1 minus n3 t3 to n3. And T32 is A32 plus S32. So basically they are radiative transition, right? And they are non-radiative transition, right? dN2 by dt is W1 N1 minus N2 plus N3 T32 minus N2 T21. And dN1 by dt is basically WP N3 minus N1 plus W1 N2 minus N1 plus N2 T21. So T21 is also A21 plus S21, and again the same drill dN1 dt at the steady state. Is equal to dN2 dt is equal to dN3 dt. So from this equation, after do all the calculation here, you can see that in generator, as I mentioned, N2 minus N1 by N. So here is the thing, N2 minus N1, that is was in minus, so that was the problem. Is 332 by 3W3W1 plus 2W3 T21 plus 2T32 W1 plus T32 WP plus T32 T21. So for N2 minus N1 greater than to be positive, T32 must be greater than T21. Lifetime of any level is inversely proportional to the relaxation rate. The lifetime of level 3 means lifetime of level 3 must be smaller than lifetime of level 2 for the steady state population inversion. Satisfied when minimum pumping rate, this is pumping rate, that should be equal to T32 T21 T32 minus T21. So when T32 is greater than T21, WPT is T21. So after many calculation, we will see that the pump required to start laser oscillation is like uh, very high. One has to lift more than 50% of the atoms in the ground level in order to obtain population inversion. Pump is WPN1H nu P. So threshold pump power is T21N1H nu P. So that is basically when N2 minus N1 is less than N3 almost 0 and N1 is equal to N2 is equal to N by 2, we assume that is NH nu P by 2 TSP. So here the problem is that we need to we need to lift more than 50% of atoms in the ground level to obtain population inversion. To solve this problem, we get 4-level laser system. The 4-level laser system, this is E1. The lasing happens between here, between E2 and E3, and this is E4. So first it goes to there, then a non-radiative transition. This is the lasing transfer happens here. Laser, and this is another non-radiative transition. This is pump. So here atoms from level 1 are pumped to level 4, then they make a first non-radiative relaxation. So lifetime order of each layer is important. So E4 and E2 has the lowest lifetime. So level 3 is the upper laser level. Usually it is a metastable level having a long lifetime. Transition from level 3 to level 2 forms a laser transition. In order that atoms do not accumulate in level 2, they and hence destroy the population inversion between level 3 and 2. Level 2 must have a very small lifetime, so that atoms from level 2 are quickly removed to level 1 and ready for the pumping. The relaxation rate of atoms from level 2 to level 1 is faster than the rate of arrival of atoms to level 2. Then one can obtain population inversion between 3 and 2, even for very small powers. So that is the key here. After doing all the calculation like the previous one, here delta N by N is WP by WP plus So level 3 has a long lifetime and E2 should has short lifetime. So this is chapter 2. No, this is basically chapter 5 of the book Laser by Ajay Khatak and K. Tyagarajan. The PDF is readily available. You can go through and read the chapter 5, you will find it. Now basic some laser problems. So before going into that, there are different kind of laser, whether it is 3-level laser or 4-level laser has been discussed in the class. You need to remember those things. The ratio of population of two energy levels is 1.059 into 10 to the power minus 30. Find the wavelength of light emitted by spontaneous emission at 330 Kelvin. So The answer is basically N2 by N1 is 1.059, 10 to the power minus 30. We know N1, N2 is exponential h nu by k dt from this discussion. Now we need that is hc by lambda kt. If we take log on both sides, we'll get the kt. So lambda is basically minus hc kt ln n2 by n1. Putting all this value, we get 632 into 10 to the power minus 9 meter, which is 632 nanometer. So we'll get question like this. We'll discuss more question in tomorrow's class. This is for today. Thank you.